Sound test. Hello everybody. I'm Erichta or Kamil, and we'll go through the last third of dynamic programming problems in CSES. I think we will go through all of them, though we did those in two streams. By the way, it was more than a year ago, but it might take more time to do those, and we'll see how it goes. There is a possibility that something like the last three tasks I will leave for the next fourth stream. And it's not that the tasks are so difficult that I cannot solve them, because I mostly know the problems here, because I, for example, cover them with my students. But it's just about the explanation. You know, the more time I spend on explanation, the fewer problems I can do. The previous parts are, for example, linked in YouTube description. So yes, they are available. I can see both chats. Okay, and thanks to Harbor Space for sponsoring my streams. In particular, still there is registration open for the Olympiad classes that I do for free. If you're preparing for IOI, consider joining. The easy group actually already started, but you can still join. The hard group will start in 1 week. I'm pasting a link now. All right, I think we can start. I'm also happy that the streams are back. Right, what do we have first? Two sets. Let me display the problem name. Two sets, two. I'm not sure if this is proper position for that name. Here you go. Your task is to count the number of ways that numbers from 1 to n can be divided into two sets of equal sum. For example, there are 4 solutions. The name contains a 2 because there is another constructive problem here called two sets, where there are multiple different solutions and you just need to split into two sets of equal sum. Here, instead, what we need to do is count the number of ways, and whenever we count or maximize, minimize, then we should consider dynamic programming. In particular here, in this task, what do we have? Well, there are numbers as well. We can go through them from left to right, and the DP is usually like this. You go from left to right, you decide about every element. For example, here you decide if it goes to set number 1 or set number 2. And you need to know, as DP state, all the relevant information. Everything that is important so far, so at the end you would know the answer. If you already for each element, let's say you went up to here, if you already for elements 1, 2, 3 and 4 decided to what sets they go, then the information that is relevant is not really which element went where, but you just need to know the sum of values. So after you decided the split of those elements, you already passed through them. Then you want to know that, for example, sum 1 is equal to 4, sum 2 is equal to 6. Actually, you don't need to maintain two sums. It's redundant information. If you know that you went through 4 elements, then here this total sum is 10. If the sum of one set is 4, then the other is automatically 6. Obviously, though, then we will look at next element and we need to know what it is. So also we need to know the current position. It's very rare that in DP you don't store the current position. So it's the position I and one of the two sums. There is also one more way how we can approach this. And here, quite obviously, the int value is what we count as the answer, the number of ways. So the definition of this DP is that, let's say that already after deciding deciding about a of I up to a of 0 up to a of I minus 1. So you are done with the first I elements. Now you will look at element I. We now look at a of I to decide about it. What is the number of ways to split those elements so that the sum 1 would get exactly this sum of values? The I goes up to n, sum goes up to, sum goes up to the sum of values, which is something like 500 squared. So the number of states here is n cubic, but it will have a small constant factor. Actually, the sum is way more limited than that, right? For every I, we can estimate how big this sum can be. Additionally, I'm going to optimize the memory. When we compute, for example, dp of 6, I don't need to remember anymore what is dp of 4. I just need to know dp of 5 in order to compute dp of 6. So always I will know just, I will get rid of this. I will not store this in memory. I will iterate I, but I know that the dp stores the previous I information. And always from dp, I will just move to new dp array. Just this dimension, maybe I will be more precise. This thing I will not store. There will be some recorded parts of those lectures on YouTube. All right. I will obviously do coding today because I want to solve the problems. What you're looking at now is virtual machine, so I actually need to also log in here. We're looking at 2 sets. And here there is modulo, there is n. Initially, both sums are 0, so I will just say dp of 0. There is one way to achieve this sum. You can pretend that this is dp of 0, 0, but actually this is index I. So we start with this. I will immediately go with a solution. So you can think about it this way, but actually I'm removing the first dimension. So this is dp of 0, 0, and then for every I, for every new value, I decide where it should go. And the previous dp array I use in order to compute the new dp array, new dp of some size. There's also here dp of some size. We need to decide what it is. Then there will be transitions here, and then we save the new dp array. At the end, what I want to output is dp of the sum of all elements divided by 2. The sum of all is equal to, there is a formula for the sum of values from 1 to n. And if sum all modulo 2 is equal 1, by the way, then the answer is 0. We can do that even at the very beginning, but whatever. In competitive programming, you don't care about the fact that in some tests you will be faster. So while I could do this logic here at the top, and it is more efficient in some tests, just to show that it doesn't matter, I'm going to do it here. Well, okay, let's not be wasteful. I will now save some seconds of computation time for the judging system. So we initially do this. If it's impossible to split, for example, 1 plus 2 is equal 3, and you cannot just values 1 and 2 split into 2 equal sums. Okay, so we have this. At the end, we print dp sum all divided by 2. In terms of sizes, well, when you have values from 1 to I, then the sum can go up to I times I plus 1 over 2. This is the max index, plus 1. By default, this is filled with zeros. We start by just an array of size 1, where this is the only possibility. And what I do here is I iterated the sum that was there so far. So this is like iterating where I'm looking at a state dp of I sum. This is the state in two-dimensional array, and from that I transition to the new dp where I can add a new value to this sum or not, because I can take it to the first element or not. Yes, the constraints sometimes are very tight. Okay, so I will say new dp of, well, I doesn't exist, of sum plus equal dp of sum, and new dp of sum plus the value I plus equal. Those are the two transitions of not taking the element to the first sum and taking the element to the first sum, to the sum of the first set. Plus equal actually needs to be performed with the modulo operation. Well, let's do it in a standard way. There are different tricks how to do it more rarely, so we can think how we can maybe abuse long longs to less frequently do modulo. But here I'm just going to do a standard thing of new dp of sum and this, new dp of sum plus I this. Not to get overflows. By the way, let's say to do, make this faster if needed. There are different ways to make this code faster. There is a typo. And let's see if it works. dp 7 8. I'm guessing that my answer is twice too big because I counted how many ways there are to choose the first set, but always every way is symmetrical. The elements 1, 3, 4, 6 can be in the first set or can be the second set. Now, if I just divide by 2 at the end, I will get wrong answer because values modulo something do not work like that. If you know that something is equal to 1, so x modulo mod is equal 1, you cannot now divide it by 2 easily. There is a way to do that with modular inverse. But the better way to avoid that is to start by saying that value 1 needs to go to the first set. So I'm going to do transitions only starting from 2, and initially I will say, let's say just this. This means that the first set does not get value 1. The first set is empty. So now value 1 cannot go to the first set. Oops, now I got too little. Why? I'm not sure why. Also, when I print 0 here, I should return. And yeah, well, I'll solve a problem I will ignore most of other questions. 1, 2, 3 can be split, so this should not be 0. What is wrong? Maybe my hack is incorrect. For every element starting from 2, I make the new array of I hope big enough size. I iterate previous things. And here I transition from sum to sum and from sum to sum plus I. Oh, yeah. I said that the division by 2, thank you. I said that division by 2 here is incorrect, and I fixed it in another way, but then I did it anyway. Okay, now I will submit, but I'm not sure if this will be fast enough, but I know ways to speed it up. Okay, accepted. And now, one thing is that we can do modulo operations slightly faster. For that, by the way, now we have 17 of 100 of second. One thing is that when you add values like that, if modulo is billion, then the new value will only go up to 2 billion. And for that, it's enough to do something like this. If new dp of sum greater equal mod, then you need to decrease it. So when you add two values modulo, then this is enough instead of the modulo operation, which is slow. For that, I usually have a function where it simulates a plus equals b, but it does this. So this is a helper function, and now those two lines I will replace with this. That's one speed up. Let's submit to see if it helped. I wish that I had an option in CSES to copy paste my code, because I'm used to that. It's faster. From 17 to 13. Definition of dp of I. Well, you're right that it's not bad to have that. So here, at this point, dp of sum is defined as the number of ways to split values from 1 to I minus 1 into two sets, such that the sum, maybe I will say here S, such that S is sum of first set. That's the definition. Okay, and final thing is that I'm guessing that because the transitions are so simple here, we don't even need a second array. We here allow a transition from value to itself, and also we allow a transition of plus I. I believe we can do it with the same array. Namely, I'm going to almost just do this. Add self, dp of sum plus I, comma dp of sum. So where, for example, let's say that I is equal 3. If you see that dp of 10 is equal to something, let's say 70, dp of 13 is equal to, let's say, 85, what you want dp of 13 be now equal to is 85 plus 70. So you simply do this. But you cannot do it in increasing order of indices, because now when you modify this from that value to this value, now representing this already represents that you added the value I. Now the definition of this is that all the values, including I, you use to split. But now when you move to dp of 16, you don't want to use this value, 155, you want to use the old value. And the way to fix that is simply do the for loop decreasingly, so that this would be computed, then this would be computed. So here from the end. And we just need to resolve the size. I will just here say dp resize of that. By default, the extra elements are 0. We have this, and I will do minus I, because here I transition to plus I. On purpose, I started from that previous code, because I think it's easier to understand. And now this is a more advanced version where, if this seems like magic to you, I recommend that later you try to simulate that for some small n. And now you can see that the time of 13 got down to 3. When you're experienced enough, you immediately go for iterative solution, not recursive. So no, those are now advanced enough problems in DP that I'm going to immediately solve them with iterative method without going through recursion first. Yeah, I have some YouTube content about DP already, you can watch that. Okay, so regarding that, I recommend later that you simulate both possible ways and see what happens. And you can think how it relates to DP, sorry, to two-dimensional DP. Oh, by the way, that was slightly faster, but of course this is even faster, right? What I'm doing here beats the idea of two tables and swap between them. But I agree. What you're suggesting here is a speed up to my intermediate code. What? Count how many subsets with values sum over 4? I don't know why. I don't get that suggestion. Also, I wonder, is there a formula, well-known formula for this? So to finish this task, let me search for that. And by search, I mean ChatGPT. I can solve this problem with DP. But is there a math formula? So I wonder if there is a solution faster than n cubic. Because what I got is n cubic, right? It's n multiplied by iterating this, which is of size n squared. I guess with FFT, maybe we can slightly speed this up. But I wonder if there is just a formula. The sequence is known and tabulated with ways. There is generating function. Consider this polynomial. Partition. Subset sum dp. So there is in OAs, or however you pronounce that in English, it's a well-known sequence, but without a closed formula. Heuristically, we do that. So there is an estimation. Yeah, sure. Okay, there isn't any formula. I didn't start the for loop with I equals 1 because I wanted to say, you know, in order to avoid double counting, I wanted to say, let's say that element I equals 1 goes to the second set. Otherwise, every split would be double counted. I will today at most go through the DP section. This will already take enough time. Actually, I already spent almost 20 minutes here, and it's just about how much I explain. If I could, I'm sure, solve all of those and talk about something else, but then you will not really get a detailed information about any problem. Your solution? I will leave this on a screen for a moment. I'm not going to read that. I believe you. I believe that it works. Let's move on to the task, mountain range. There are n mountains in a row, each with a specific height. You can glide from mountain A to mountain B if A is taller than B, and I'm guessing A is taller than all the mountains in between. What is the maximum number of mountains you can visit on your route? Already, even without thinking, my first thought is that maybe it's easier to do in reverse. I don't know that, but we'll see. This relation is not symmetrical, so we need to consider going from left to right or going from right to left. Also, actually, it's not even that we go in some order, we can go left and right. Let's make sure that I understand it using the example. So I will copy this. I start somewhere, let's say it's 35, not necessarily the maximum, 40 is the maximum here, but I can start here. I can glide from here, from something of height 35 to something smaller, for example to 20. Then from 20 I think it's allowed to glide, for example, to 15, and you can stop here. You maximize number of mountains you visit. So it's not DP from left to right. The order is that we go from big values to small values. Of course, we can also visualize that. There is something of height 20, then there is 15, 15, 17, 35, and so on. And it's legal to go, for example, like this. Just as long as physically there is nothing taller in between. I see how it can remind you of a convex hull, but it's not, we don't care about angles. We just care about the comparison. For example, convex hull for such 3 points would say, maybe I will make this slightly bigger. A convex hull for those 3 points would say that there is no way to get directly from here to there because there is this point in between. But here that statement doesn't mention that. It's not that we go with straight line. We just care from here we can go there as long as other things are below. Because of that, it's not convex hull. And by the way, yes, in that previous question, you could divide by 2. But I did a trick to avoid that. I mean, if we went only in one direction, I agree it would be monotonic stack most likely. But here my thought is that we will go from big to small values, and because of that, stack doesn't make sense. The order of DP transitions here is not from left to right, like in the previous task, for example, we went through the sequence. When you go, because if there is even a big sequence, it's possible that from here we go there, from here we go there, and so on, right? It's very complicated. For small n, maybe it would be some kind of range DP. But no, n is big, 200,000. Because of that, I think we need to sort the values from biggest to smallest, or from smallest to biggest, and do something in this order, I think. For example, starting from maximum, let's say maximum is here, the DP will be the answer, which is the number of mountains visited so far. So for this guy, the answer is 1 right now. You can visit 1 mountain and be here. And then for everything else, you can mark it as value 2. Because from 40 you can get to anywhere, assuming that there are no ties. Right? Maybe there is another maximum. This would be a small issue. But for a moment, let's assume that numbers are distinct. So I will maximize this with 2, maximize this with 2, and then I will move to the next maximum, like maybe 35 here. And I need to then maximize this range with 3 and maximize this range with 3. So I think my solution will involve sorting values from biggest to smallest, iterate in this order, maintain something like a set of already visited things, because in that set I want to know, like for 35, I want to know the next to the right bigger position, the next already visited position, to know how big of a range I maximize with 3. I guess it doesn't hurt. I don't need to exclude myself. I'm going to just simply maximize everything with 3. It's cheating a little bit, but this value will not be affected in the future. So this, and we need to here maximize the range, which is like seg3 maximize operation. Segment tree maximize. And now I wonder if there is a simpler solution. And yes, I see how this is some kind of range DP, but I wouldn't really call that range DP. Yeah, you can glide left and right. Somebody mentioned 2 monotonic stacks. So do you claim that this solution is solvable without a segment tree? Oh, I know. Let's be smart about using AI. I will provide this task. Now, this is very dangerous. I think we cannot be 100% sure about the correct answer, but can this problem be solved in O of n? Answer yes or no. No more explanations. I just don't want spoilers. This is one question that I have. Yes. Okay, I wanted to then ask, I expected a no, and then I wanted to ask if it can be done without segment tree. Yeah, you got without segment tree, but in linear time. By the way, I thought that maybe we can avoid something like segment tree, but still we need to at least sort. Okay, let me think. People keep mentioning monotonic stack, so let me think out loud. I don't want now, no further hints, please. I will assume I will try to get a solution. And I hope that also the part of me trying to get a solution is educational. I believe that if from some position we get somewhere, then it's not possible to, it's only possible from here to continue to the right or to continue to the left, but smaller distance. If this is 50 and you move here to 40, then from here you cannot exceed 50 again. You need to move to smaller value, like a 30 here or a 30 here. Okay, you will, I think, never jump from 50 directly to 30 if you have a 40 in between, and you can indeed jump to 40. Right, so you only, it only makes sense to jump from 50 to 30 if only smaller values are in between. I'm again not sure about ties, but for some time now we assume only distinct values. Assume only distinct values. It's a simplification, and maybe I will get some ideas that will not translate to ties. I use 3 monitors. For streaming, it's convenient. For everyday work, I prefer 2 monitors. I turn off the third one. So when do we even move? So from 50, I think, to 30, I will only move if things in between are smaller or strictly smaller. So this will be, let's say, 29 and below. Now, if there is somewhere here value 25, can I greedily decide which element is better? Is it always better to get to 30 because from 30 always you can get to 25? It seems so. Okay, what about that? If there are only distinct values, isn't it true that from 50, from the maximum, I will just get to the biggest value on the right or the biggest value on the left? Isn't that enough? So if this is 40, then here's a lemma. I will only move to 35, which is max on the left, or I will move to 19, which is max on the right. And I continue the process here. From 35, I only move to the maximum on the right, which is 25 in this remaining range, or maximum here, which is 20. And so on, continue the process. Maybe also we should look at it from smallest to biggest. Maybe that's simpler. But that's already a solution, more greedy solution, not really deep, well, more greedy than DP. And for a moment, I'm not worrying about ties. Now, what if I look from the perspective of smallest values? Does it change anything? Maybe from... It seems that if you look at a small value, like let's say 15 here on the left, isn't it true that you always get here from a neighbor of yours? Like 17. If the last step is to get to 15, then why would you go from far away? Doesn't make sense. I think it's always better to visit something in between. So at the end, it seems that we will do just this step. And is it true that we will, if the values are distinct, is it true that always the solution just looks like this, where we visit all the values in some range? Like here, 15, 17, 20, 35. Oh, but here we can skip something. So not everything in a range. From 15, there is a neighbor 17, always the smaller of 2 neighbors. Then we have 20, then we have 35, and then we have 40. So if you know the last element where it's optimal to be, I think you look at next greater element to the right, next greater element to the left, and you choose the smaller of the two. So from 15, you choose between 17, 20, you choose this guy. From that, you choose between 20, 35, you choose this, then 35. Then you skip this because always you look at next greater element to the right, which is 40. No, I don't think that is easy. No, I don't think it's that easy. Are you sure that solution doesn't require sorting? That would be of n log n already. Let it think. By the way, I am experimenting with how to use ChatGPT to, make a competitive programming practice better, and also the streams. I mean, okay, then it's not O of n, it's more like O of square root of the max value. Why am I looking at this problem? Oh, because I'm looking at a virtual machine. Well, I don't really want to spend more time investigating this if it's not really DP. Yeah, so I'm referring to this comment too. Oh, wait. Yeah. I mean, it's not that I'm entirely happy about getting hints anymore because I wanted to try it myself. But now that I'm talking about this thing with for every element, you need to know the next greater to the right and to the left, that can be pre-computed information. So we claim that for any element, if somewhere in the sequence there is a value, let's say 20, then we wonder how we get there, from the right or from the left, from something greater. And if you certainly didn't get there from something small, like here 7 and 8. If here there is a 30 and here there is 25, then 25 cannot get to 20 because there is bigger in between. If there is something bigger here, like 40, then it's from 40 you don't directly go to 20, you pass through the 30. Also, if there is 30, then you also from this guy can go. So it seems that to an element you get, you only can get there from the next element to the left that is strictly greater than you, and next greater element on the right that is strictly greater from you. And those are your only transitions. We can pre-compute that with one linear pass from left to right and one from right to left. There's next or previous greater element. And by the way, what ChatGPT answered is yes, it can be done in O of n without sorting, which I'm still surprised by, because I know that we can do transitions this way, but then still we need to emulate the DP. Well, I'm going to now implement this idea of mine. I don't think I will share my codes with you today. I don't think it's really valuable. Like, you see my codes. If you really want it that much, you can rewrite it. I don't think you need my code. So I will keep using the same file. Yeah. Going from left to right, I want to, for every element, find previous strictly greater element. And there is O of n solution for that. Let's make a function. I mean, for educational purposes, I will show you how to do it with a sequence reverse, though it's annoying, and during a contest I wouldn't really do it this way, but it's educational. Find previous greater. Let's, I don't know, pass n, whatever. Find previous greater. As you go through, do I need the index? Yes, I guess I need the index. So as you go through this, through the elements, you maintain a stack of previous values that could be the previous greater element. And if already you passed through one and then you have a 5 and so on, then 1 should get erased. But if you see a situation like this, 10, then 1, then 5, and then you will look at the next element. For this next element, the previous greater can be 5 or 10. Both of them you can keep in a stack. I usually just use vector of pairs, V. First, put some kind of infinity there for convenience. It's called sentinel to avoid runtime errors. And for every new element, just like 5 would destroy the value 1. So while v back dot first, let's say, is smaller or equal than myself, like here it's the situation, then you want to erase it. And v dot pop back, and then v push back or place back myself. And here we know that previous greater for I is equal to v dot back dot second. We get that index. For example, if there is a 3 here, the vector would contain those two elements, with this being the most recent one, the vector dot back. And then for this element, we say for you, the previous greater is this. Okay, we return previous greater. And now I would just implement this again, I think, from right to left if it was a real contest. But the nice solution is that you can now say previous greater is equal to this find previous greater. Then you can reverse h. You can run the same function again. Now this next function you need to also reverse because it's computed on a sequence in reverse. For safety, in case I need to use h again, I will also reverse it back to the original form. And also for next, the indices are messed up. So for every index inside of next, I will say I is equal n minus 1 minus I. I think it properly switches between counting from 0 and counting from n minus 1. By the way, I'm guessing that the next DP problem will be easier than this one. This seems quite difficult. I need to also create this array. All right, let's copy already this input and let's see this. And I want for every position, print the previous. I is equal to this. I want to verify if so far we are okay. Previous is equal something, previous of I. Okay, for example, the last element, the previous is 8, that's correct. For this element, the previous is 7, correct. For this element, the previous is 2 units ago. Indeed, that's correct. And there are some minus ones. Okay, what about next? Next greater element. For 9, the next is 8. That's very stupid. Wait, does this achieve anything? Oh, yeah, I'm not printing next. the reverse trick is especially powerful if you're doing something more complicated. Okay, for those, so if you know you do something 50 lines of code, then you don't want to do 50 lines of code again in reverse. You want to do a few lines of code in order to just have a function that achieves the complicated algorithm. For something as simple as what we're doing here, I think that we are risking a lot doing a lot of reverses, doing this. This is also dangerous. But I think you should practice in such a way that you optimize your performance in hard problems. And in a hard problem, this 5 lines of code to avoid repeating some complicated function is worth it. So for those, next is 10, for this guy next is 7, for this guy next is 10, for this guy next is 5. Seems good. All right, and what now? And by the way, the -1s and 10s, it just means that something is outside the array. So for example, for 40, next greater element doesn't exist. Oh, also let me test 3, 10, 10, 10. For each of them, next greater doesn't exist. Good. And now the DP part. I don't know how to do it otherwise, so I will just sort the elements. So now collect all the values in a vector. Let's say vector of size n. For everything, v of I is a pair of h of I comma I. Now I want to sort them decreasingly. Decreasing sort. So from biggest to smallest. And in this order, for every element, you know that you transition here from the 2 bigger values, the previous and next. Also, you create DP array. By default, filled with value 1, because everything is a single step already. You maximize number of visited mountains. At every position, you can start, and you can say, I visited already 1. I mean, this is DP, but DP seems to be, you know, like, I don't know, 10% of the difficulty here. The hardest part was figuring out how to do all of that. So observations, not that much DP related. Okay, now in this sorted order, for everything in V, this is a pair of value comma index. So I'm interested in the second element. And in this order, I want to do DP of I, and I want to maximize, I want to do this, next of I. It's just that those might be invalid. And I think I will just do it with 2 ifs. If previous of I is not -1, then DP of I maximize DP of, or maybe let's do it more as a one-liner. Here I will say, if previous of I is equal -1, then use 0, otherwise use this. So this means if this is -1, use that value, else use that value. And similarly here, next of I is equal n, then use 0, otherwise use that. At the end, print max element. Zero, beautiful. +1, +1, +1. Right, we transition. If I was somewhere with 3 steps already, then here I'm with 4 steps. 5. Okay, one last thing. There is a way to do this in one line, right? I will, again, as part of my learning of using the AI properly, I think that chat also, you would guys be able to help me, but in C++, when I type this vector int I, maybe int A is p dot first, int B p dot second, how do I simplify this to one line for loop? Thank you. Yeah, I figured that somebody from the chat could also help, but also I just want to get better at using AI. So I'm learning. Okay, so there are those two options. I'm not modifying it, so the reference doesn't matter. Okay. Now, where am I? Here. So it's better to do auto, or it could also be a pair, right? So this is valid, pair of int of now the value which I don't care about and the I. So is this valid? I will just get a warning that value is not being used. Interesting, this is not a pair. What is it then? Okay. Okay, I will now submit this. But also I want to learn the actual type. What is the type of this AB pair slash tuple? What I can replace auto with? I mean, no, for just a pair of integers, the reference is, there isn't any significant difference. Interesting. It's a structured binding declaration that introduces two variables. So it seems that you cannot replace auto with anything. I thought that auto is always just a simplification for I'm too lazy or I don't know the type, but that's it. But it seems that here auto is more powerful. Well, good to know. Okay, solution is accepted. And now, okay, how to solve this in O of n without sorting? Because I did n log n at the end, I can replace it with something that is based on the max values, but that is not O of n, it's O of square root of max value. Recursion with memorization. You might be right. You might be right. Good point. Okay. Okay. And they are saying that this is a tree. So we can store it as a tree and then run something like DFS to find the depth in O of n. This is essentially a max Cartesian tree. Just so you would understand a little bit better of what that might mean, I'm going to show that such a sequence, if we care about maxima, then it can be represented like this. 40 is the biggest, then the biggest on the left here is 35, on the right is 19. I hope that I'm right, that this is what this is about. Then 13 and 12. Right? Can somebody confirm that this is the Cartesian tree? Also seems to be binary search tree. And here the height of this is equal to 5. But what does it have to do with, for 17 I searched for the next greater element on the left and on the right. That doesn't seem to be exactly the same as what I computed. But I agree, if we store the tree, then that's it. But I think I like more DP related seems to be the suggestion from, who suggested that? Wait, I'm going through the chat. Yeah, the Gosunov suggested recursion with memorization. So I actually want to implement that. So forget about the tree. So one more solution. So we do those transitions, we know them, and now instead of sorting, it will not be faster in practice, by the way, because memorization, I mean, recursion generally has some overhead, so sorting might be equally fast. But instead of this, I want to say for every position, answer is equal max of answer and some kind of f of I, and then print the answer. And this will be dp with memorization, which includes this. And let's say we also know the n value. Those I will pass by reference. I cannot copy big structures, that would be slow. And now if it's already computed, if something, then return that. For that, let's say dp, I will fill it with some fake value like -1 or 0. Yeah, 0 is fine. So I will here say dp resize n. And here, if dp of I is already computed, then return it. And otherwise, let's say I get this. By default, me is 1. Return it. This is convenient. It's a reference to this so that I wouldn't need to keep using dp of I, which might be annoying in multiple transitions if you have a lot of transitions. And then if previous of I is not -1, then me is max of me and f of that guy, n plus 1. The only reason why I passed n here as argument is that I will now need to check if next of I not n, then do this. Now I think about it, n also is the size of the vector, so I don't really need to pass it, but whatever. Me 1 plus f of next of I and previous next. And now we don't need this. Do I have a file? Yeah, I do have a file. Why do I keep copying it? Seems to work still. Cool. I'm very happy about the fact that we spent more time on this problem. Actually, investigating different solutions was maybe not very valuable at first, so trying to solve it, but I'm now happy with the final solution of, for every element, find the previous greater and the next greater, and now use recursion with memorization instead of sorting. Somebody asked me here in the chat an hour ago whether I will only do iterative, and well, generally 95% of the time it's better to do iterative. You have more methods at your disposal. But one of the rare reasons why you might want to use recursion is that the order of iterating things is difficult to decide. Another reason sometimes is that only some states are possible. Not all of them. Not all from 1 to n will be visited. Then also you should use recursion. I don't think there is an official editorial. There might be something unofficial. Yeah, I mean, if I explicitly construct some kind of tree, then with different ways, including DFS, but also BFS, I can do this. I see this refers to the drawing. And then I will leave here on the screen for a moment some notes from Solaris, but now I want to, for the sake of recording of this stream, but now I will continue to the next task. And yeah, it's interesting that I also actually, for me, it took seconds, to be honest, to come up with the quite complicated and slow solution involving segment trees, but eventually, which I did discuss at the beginning. Wait, I need to let the dog in the room. Oh, there is a tutorial. Analog and solution. This, and what do? We use a set, right? Or just a map? This map simulates a set, I think. Yeah. Then we do something. Do we also, okay, we go in decreasing order, we do this, but without the, I mean, my segment tree solution didn't use any observation about what transitions are optimal. The segment tree was just, from this you can go to this whole range. Linear time, use stacks, then we create a graph, and topological sort. Yeah, so they, instead of recursion, they want to use iteration at the end, but if you don't know, if you, without sorting, want to know the order of operations, but you know all the transitions, it's a directed graph, and you can topo sort to get information about the order of iterating it. Actually, that seems to be overkill. I think instead of this highlighted part of topological sort, usually it's just easier to do recursive solution with memorization. But sure, this might be faster because, as I said, recursion is slow, big constant factor. Also, I'm sorry that I'm so stupid that I didn't try analysis tab for the editorial. And I see that now 10 people wrote to me about it. Yeah, I hope not to call myself a YouTuber. I'm a teacher. I teach algorithms. Just YouTube it's like if I use Zoom, let's say, for teaching, I wouldn't call myself a Zoomer. Similarly, just because I use YouTube to teach, I don't want to call myself a YouTuber. We are 1 hour into the stream, and we solved, ladies and gentlemen, 2 problems. I think it will be reasonable if we don't solve then all of them today. I think it's better to talk more about the problem, to actually cover it, instead of just rush through it. So the current plan is to do only some today, and then there will be a 4th stream. Cool stuff. Actually, remember this. I mean, it's not that it's crazy important, but DP is always, well, would I call DP part of graphs? Yes. I mean, okay, a simplification. Dynamic programming is category of graphs. Okay, it's not exactly equality, but every single dynamic programming problem can be represented as a graph. State is node, transition is edge. And they are crazy related. It's this almost, you can say, that is equality. It's more like DP is part of graphs, I would say. Where iterative usually means that the order of nodes is trivial to do, and recursive often means that the order is more random and it's not just from 1 to n. But in particular, something like Dijkstra, you can try to understand that, yeah, sure, it's a graph algorithm, but it is dynamic programming. And the only reason why Dijkstra we don't do in for loop from 1 to n is that there is some unknown order of visiting nodes. So it's DP like for loop, but more complicated. And here in Dijkstra, priority queue allows us, as we simulate Dijkstra, to know that order. So here in Dijkstra, we cannot separate the parts of first we decide the order and then we do a for loop for that, because this is actually the same part. We need to run the algorithm to know the order of visiting nodes or states. So Dijkstra is both DP and graphs. I think it's useful to be aware of that. Huge, congrats. Thank you for all the help back then. And I mean, okay, preparing, if you mean that you already got an internship role, then congrats for that. And if you're saying that you're preparing and you hope to get such a job, then I wish you all the best. Good luck. Cool as well. What on the screen now is sans serif? Is this sans serif? What font is this? Well, I think we will not, by the way, do any DP on trees. So this font is Arial. Oh, wait, what sans serif font that matches Arial? What does it mean? What is Arial versus sans serif? Okay, this is category of fonts. Anyway, I don't care. I mean, I'm okay with reading this. Let's move on. Increasing subsequence. You're given an array with n integers. Find the longest increasing subsequence, also called LIS, longest increasing subsequence. Where every element is larger than the previous one. And subsequence, it means that you take some elements. For example, you take 3, then 5, then 6, then 9. This is, I think, here one of the longest increasing subsequences. There are a few solutions, including, for example, segment tree, but I think it's best to first understand the easy DP solution, where as we go from left to right, for every element we want to know the best answer, the best length of sequence up to here. For example, 5 is after 3, so there is a sequence of length 2 ending with 5. For this 6, there is a sequence of length 3, which is 3, 5, 6, ending with 6, and so on. So let me first implement the quadratic solution, and then I will talk about n log n solution. You mean a sorting solution for increasing subsequence? I don't think it helps to sort this. You get an equivalent problem, I think. Okay, so quadratic solution first. Which will get time limit exceeded, but that's okay. For a moment, it's okay. I want to say dp of I is defined as length of longest increasing subsequence ending at position I. By default, everything is equal to 1. And now for every element and every future element, this only iterates elements to the right. If the next one is greater, then I can do transition, I can extend, meaning dp of j is maximized with dp of I plus 1. It's maximum because there might be many possible transitions to the same position, and we choose the maximum of them. Print max element. Now, this is quadratic, obviously, because we have two nested for loops. Party sorting without segment tree. I don't know that, so I will not cover it. Oh yeah, good point. Good point. There is AdCoder beginner contest soon. It starts in 40 minutes, 42 minutes. So consider registering. I will not participate today, and I will not cover those problems. All right, and now for one of the solutions, we know, as we go through this sequence, we know that there is at some position, actually position doesn't matter that much, but the value matters. There is value 7 with dp answer of 1. Then there is value 3 with dp value of 1. For both of them, there is a sequence ending with it, a sequence of length 1. And then there is something of value 5 with dp equal to 2. Well, after iterating those three elements, this is what we would store. And here, this element can be forgotten or destroyed. Forget, because among those two it's always easier to continue with a 3. After 3, if there is something, it will create a sequence of length 2. After 7, it's only harder to do it, and the dp length is the same. So if you see 7 and then 3, you can forget about 7. It will never create a better answer, a longer increasing subsequence. Okay, and because of that, what will happen is that as we keep visiting new elements, for example, there is a 6 here, this will always be the situation. So this is what we will store. And sometimes when new value appears, like let's say that now there is new element a of I equal to 4, then those are our candidates. Also, let's store there is 0, imaginary 0 with dp equal to 0. For this value 4, we need to consider what it can follow. After what element we can get a 4? Well, after each of those elements. And in particular, this is the biggest of them, the 3, being at the end of sequence of just a single element. And now we can say that after that there can be a 4. So then there will be a 4 at the end of a sequence of 2 elements. And now we can erase this highlighted part because it's strictly worse, right? If we have 2 sequences of length 2 ending with 4 versus ending with 5, then this is better. Okay, and then we continue. I don't need to consider continuing other states with this value 4 because it will be only worse. After 0 elements already, I can have a 4, but it's better if I am to have a single element to have a 3. So always a single transition should be done. And generally you have always a sorted sequence where you can binary search to see which element should be continued with this value. Like here, the sequence is now 0, 3, 4, 6. So I will just store it in an array that looks like this. And if now there is element, let's say 2, you binary search here what element can be extended with this value. So what is the biggest element that is smaller than this? And the next element you minimize with that, or you replace. Yeah, there are different solutions. Now, the task is so well known, longest increasing subsequence, that if you want a more detailed information and simulation on some example, I'm sure you can find it online. But I will just do it here. We start from just a single element 0, and I will not even store the input, to be honest. Just I will repeat n times of read the value. I will not store it in any array. I will now here binary search there. For that I will lower bound the value x. Lower bound finds me the first value that is equal or greater. So I know the previous element was strictly smaller. Let's say here for 0, 3, 4, 6, if I lower bound on 5, this would give me lower bound of 5 would give me the 6. So I know that the previous element can be continued with 5, so this element I replace with a 5. So the position is this. From iterator, this is how you can get the index in C++. And now dp of I is just equal to x. You don't need to type minimum because you know that this element is greater or equal. So it's always better. Though this is also valid. You can type this, but you don't need to. You can just say equals x. And finally, if I equals dp size, then dp pushback, I don't know, something like 0 or infinity. Otherwise, this would give you runtime error. At the end, you don't really care about the values here. You care about the size of this array, because this corresponds to a sequence of length 0, 1, 2, 3. So just the last index. You need to print the index of the last element of the array. Time complexity is n log n. Seems to work. I mean, so first of all, to answer your question, I think that somebody of 2000 Codeforces rating might be able to do everything in CSES, given enough time and also time to, search for stuff, like to search for some algorithm. That being said, it's not optimal. So if you're asking to know what you should do, then you should just keep solving problems, and eventually you will get to a level that is just too hard for you because every problem takes so much time. Yeah, if you're advanced enough, then segment tree solution here is simpler to understand. But the advantage of this is that it's very short. And if you are experienced enough, then you should understand multiple solutions to well-known algorithms, because there might be a difficult task that will require one particular method to solve something basic, and only that one method will be extended into the full solution to a hard problem. So at my level, I know that there are multiple solutions, and I'm aware that it's useful, the knowledge of multiple solutions, not just one. How to reconstruct from the array? For that, it would be useful to actually remember more stuff, like keep some kind of parent array, also called breadcrumbs, where for every element, if you know what it should follow, then you should, for an index, remember it goes after what other index. That's how you, I think, can then reconstruct. That's, by the way, common answer to how can we reconstruct some DP subsequence. Yeah. And I think I will not spend more time on this here because we have also other problems to do. And maybe some other day I will do a live stream specifically about LIS and its different solutions. CSES is actually good for making sure you know well-known algorithms. It shouldn't be your main practice method, but you should include CSES in your practice. 3 problems today. We are doing like half an hour per problem. Not great. Projects. I mean, not great for my initial plan of solving everything today. There are n projects you can attend. For each project, you know its starting and ending days and the amount of money you would get as a reward. You can attend only one during a day. What is max amount of money you can earn? Okay, so we are given ranges, each with a value, like a reward. And for example, there might be a range from here to here, giving you a value of 70. There might be something from here to here with a value of 5. There can be something from here to here with value of 80. Maybe there's something there with value of 20, and so on. And now you need to choose disjoint ranges. Choose disjoint ranges to maximize the sum of values. For this input, optimally, we would choose white and red. 70 plus 20 is in total 90, and it is optimal. Well, it's hard to do this in another way than from left to right. And always when you look at a range and you consider maybe I will do it, I will take it, I will use it, then you know that you can continue only starting from after that. So what you can do is, if you start from here, you know that so far you got a reward of 0, plus 70, that's 70 in total. At this point, just after it ends, you can say, from now on, I have a possible answer of 70. And here I have a possible answer of 0. As you keep iterating, when you are here at the start of another range, you're always interested in what is max value so far, like 70. And if here, when you're here, you have 70, you say, when I'm there, there is a possible 90. Right. I think we can describe that solution as a sweep line, though I'm not sure if it's the best name. So we sweep the drawing. We go from left to right for the events of like range start, range end. And always we do something. When the range ends, we just have a new possibility of what is now the current answer so far. And when range starts, we read from what is the best answer so far, like this 70. I don't know if I would exactly call this solution a DP. I think it's more sweep line than DP. This is the thing I'm talking about. But yeah, it's DP-like, DP adjacent. If you're new, if you want to do CSES, you should start from the first problems. And there is a book, Competitive Programmer's Handbook, which goes with that. It's a free PDF online. Is there, by the way, a solution that is less about sweep lining? I don't know. So is there something that really looks more like DP? For everything, you have the start, end, and the reward. I prefer to call that LR and the value P, whatever. And now there will be some kind of events that I will sort. The values are up to 1 billion. I will make a struct for event. It's either start or end of a range. So there is a position, X. Maybe let's call that position. There is the type, 0 or 1, the start or end. And if two things are on the same position, then in what order should I do it? Starting and ending day. Oh, it's not clear from the statement. So 4, 6, 8, 7. Okay, here it should be clear. If I have a range 3, 6, after that it seems I cannot do 6, 8, because then the answer would be 6 plus 2, which is 8. But the answer is 7. So I cannot start a project on the same day I'm ending another one, which means that at 6 I should first process that this guy starts, and only then I should process that this one ends. If instead I first consider this guy ending with a 6, with value 6, then I will consider this new range from 6 to 8 with value 2, with 6 plus 2, 8 in total. The answer would be wrong. So I need to process the start first in case of a tie. And let me do exactly that in the code. The type start is 0, end is 1. So this is the type start or end. And I need to sort the events. For that, I will make a comparison function, the smaller than operator, to do my own custom comparator. And here I will return whether my position comma type is smaller than his position comma type. It's a nice trick where the pairs in C++, like vectors, are compared by the first element, so by the position, and in case of a tie, by the second value. And with me numbering them like this, start is smaller than end. So at the same position, start will be considered first. If I do this, it will have a different behavior. Now it's the opposite, which means that I could do project ends on day 6, and only after that some other project starts at day 1, and that would be allowed. But I want this. Okay, and there will be, I'm guessing, also the ID of the project. But it's not used for sorting. It doesn't matter. Okay, we have the events. Here, events, pushback, event. At position L, we have the start, and we have this index of the event, of the range. And at R, we have the end. Then we sort. And then we need to maintain the max reward possible, like the answer. Max reward possible so far. Among all the events, we are at some position, we have the type. I'm interested in the type and the index. If type is start, if we are at the start, then I know what is the best so far, the best sum of ranges before, and I need to save it for this range. I need to know that when this range ends, let me show using a drawing. So when a range starts, like this guy starts, it knows, oh, 70 was possible before. So I save this 70 plus 20, which is 90, and I need to use it at the end of myself. So I need to here say at end of myself is equal to the answer plus my own value. And I need to save it. So, well, let's say also in the event. It's a little, it might be redundant, but well, why not? It's not that it will use a lot of memory. It will not be crazy memory usage. Plus event.p. And else, if you're at the end of something, you will use at end of I, and it's enough to just do this. At end. Did it compile? No. Uppercase R. Sure, ID. I mean, this kind of mistake is very easy to notice, right? The first time I compile, I will notice. I'm not reading the chat. Confirm. I can confirm that I'm not reading the chat. Never did. Yes, I I overrode the smaller than operator specifically for those structs or classes, so that sort would work. If I didn't do this, then sorting would give me compilation error because it wouldn't know how to do it. I don't have strong. I didn't read that book, so I don't know, and we don't use binary search here. Okay, now analysis. Do they do sweep line or something else? Yeah, sweep line. Well, is it really DP? Oh, cool. There are references. Oh, but it's just reference to the full book. Oh, chapter 30. At least that's some information. So there is PDF. Chapter 30? Are there 30 chapters? Indeed. Sweep line algorithms. That's cool. Though this chapter actually, I don't think it's a great chapter on sweep line. I mean, it talks about one problem about ranges, but then quickly it moves to intersection points, and then it's too brief, I think. Yeah, not perfect, maybe. What was that? I recall the name, repo Frowns, but yeah, I don't remember now, so I cannot tell you. I mean, I did custom sort, right? And then you have two choices. You can do operator here, or you can do it here inside of sort. I think that this is nicer to do. You mean that this sweep line thing or what? Okay, now first thing is that be aware that EdCoder beginner contest starts in 20 minutes. Second thing is I need to now decide how long this stream should be, because we are left with 4 problems here. I mean, one possibility is to finish the stream now. We did 4 problems, and I did a lot of explanations. It took almost 2 hours, but maybe this one is fine too. Okay, let's do this problem. If you need to go to, if you wanted to participate in EdCoder beginner, then please do it. In 20 minutes it starts, and you can, you know, rewatch it later. But I think after elevator rides, I might stop the stream because the next problem is complicated. If I am to explain it properly, it will take a lot of time. The tilings problem. Okay. I very much like elevator rides, and I think, well, let me open it here. I'm using virtual machine, so sometimes which browser I'm looking at is not trivial. Okay. Done. Now we are looking at 2 windows, 2 tabs in Windows. I mean, it depends on the explanation. Oh yeah, that idea. I agree. That idea is nice. There are n people who want to get to the top of a building which has only 1 elevator. You know the weight of each person and the maximum allowed weight in the elevator, so the capacity of elevator. What is the minimum number of elevator rides? N is up to 20. First thing, if n is up to 20, you don't even need to read the statement to guess that most likely the time complexity will be this, maybe times something. Okay, easy. Then, so this might involve iterating subsets or having bit masks. If you don't know what a bit mask is or binary mask, then this problem is not really available to you. You need to learn a lot of other things. But assuming that you knew already about this and you just want to solve that. Also, let's be aware that this is kind of multi-dimensional knapsack problem, where there is a knapsack or here elevator and we want to pack elements inside. For example, here we have the X, let's call it W, maybe not. Okay, X. This is the knapsack capacity, 10. And here we have people with, the order doesn't matter, as well I can sort it, but also that's not very useful. Here it's optimal to send 1 with 8 in one elevator for the total value or weight of 9, and 4 will fit with 6. Generally, for knapsacks, there are no existing correct greedy solutions, and generally all the solutions are exponential. They either use the values, which are here up to 1 billion, or they iterate exponential number of possibilities, but here it's fine because n is up to 20. If n was here up to 100, then there would be no solution. Maybe something heuristic that happens to be fast enough. Now the dog wanted to go out of the room. All right. First thing that you could try, but doesn't work, is that if you have your sequence of people, the sequence of values from the input, you can go from left to right, which we often do in DP, and for every person we can decide about this person, which would mean here that we decide to what elevator it goes. But then the state would be how much every elevator is packed. So like elevator 1, elevator 2, elevator 3, and each of them goes up to 1 billion. That's not really viable. No, I'm not a Twitch partner, so you cannot subscribe. You can follow. Yeah, the dog hates bit masks. He only wants polynomial solutions. When he hears about exponential solutions, he just wants to hide. So that's not available. Instead, we want the state to include the binary mask of people. So maybe that should be it. Then int dp of here mask of people already used, it can be equal to the number of elevators already sent, right? The int being the answer. For example, if here we have 4 people and I can send, let's say, this one with this one, then one possible way to look at it is that dp of a mask 1010 or 0101, whatever, is equal to 1. Meaning that I can send the people represented by those bits with a single elevator. And the final answer, by the way, would be dp of 1111. This is pseudocode. Those are binary operations. Okay, but what about the states? Well, one possibility is that then you can, for every state, iterate what people you send using the next elevator. So what you can do is you iterate the masks for every mask, and there are 2 at power n of them. You here are looking at this state and you want to do transitions. That's mask of a next elevator, which people you will send next, and you do here the transition from dp of, let's say this is mask 2. From dp of mask you will transition to dp of mask or mask 2. This seems to be 2 to the power n times 2 to the power n. Actually, there is a way to prove that if you only iterate submasks that don't have anything in common with this thing, it's actually 3 to the power n. But I will not go into detail about that because n is so big that we need to get 2 to the power n. So we cannot do transitions that are also exponential. We need to focus on packing a single elevator. Now, my issue with this problem is that I covered it so many times that I remember the intended solution, and the intended solution is this. I would call that partial DP, that's how I call that solution, but the more straightforward solution has this time complexity, and I always forget about what it is. You know, if you solve a difficult problem and you spend enough time on it, you might not remember the brute force. This is always the issue for me. So I'm trying to remember this guy. I'm assuming that it will be 2-dimensional DP. Oh, I know. Okay. If we want to speed up the transitions, I want to always send a single person. Okay, but some people are already sent in previous elevators. So let's say those are sent already before. And now what I'm doing is I'm building the next elevator, and I want not to exceed the total capacity X of the elevator. And for that, you want to store the value, the sum of those. I'm going to say that there will be that what is included in this DP state is mask of people already visited, and I actually don't care which ones were visited in previous elevators and which ones are visited in current elevator. For me, it will be just one mask, so it will be just big, 1 1 0 1 1 1 1 1 0. Some of those are now in the elevator that I'm still filling with people. So there is mask of people. For the current elevator, I need to know the current weight or remaining capacity. And also I need to know the answer, the number of elevators. And this is the only small value, so I will, okay. And there are different ways of which of those values are the dimensions and which are the value of dp. For example, you can say that this answer is the int value, and here you have mask and current weight. That's not available. This is 2 at power 20, this is 1 billion. But you can swap those two things. You can say that this is the current weight and this is the answer. So here, this is answer, which we minimize, the number of elevators. But instead, I'm going to do in the dp of mask and answer, and here that's current weight, which we also minimize. The fact that here both we minimize doesn't matter. I could here decide separately. So I want to know the following. And I prefer actually to have smaller dimension first, because of how we will iterate them in the code. If you have multiple things in your state, multiple things are relevant for the DP, because DP is a way to speed up some process. Here the process is that you keep taking a single person, putting them in elevator, and sometimes the elevator is, let's say, full. You want to be done with it and you move to the next elevator. Right, so now those are the relevant things, which people you already used, the weight of the current elevator that you keep building, and the number of elevators, the answer. Because this is small, goes up to 20, the number of elevators, because there are up to 20 people, it's better to use this as dimension and something else as the value of dp that you minimize or maximize. Now, mask couldn't be minimized or maximized because you don't compare two masks and choose the smaller one. But the current weight of elevator, we can minimize. Because if you have an option, let's say option 1, people 1 and 2 and 5 and 6 and 8 are already used. We send 2 full elevators, and third elevator is already, let's say, 20% used, meaning 20% of the capacity is used, versus you have option 2, where you have the same everything but 25% is used. Then obviously option 1 is better. All the other parameters are the same, but the current elevator that we built is less used, so it's better, meaning that we can minimize that value. We can say is something used, and the something here we minimize, given the same mask of people used and number of elevators fully used. Hence, this is a valid DP. The memory complexity, it can be optimized, but it's 20, so n, multiplied by 2 at power n. But then there are transitions, and for such a state, you then iterate the person to use. Any person can go, and suddenly it's times that. So that's surprisingly unless you maybe spent a lot of time optimizing, you will get time limit exceeded. I don't think here binary search is useful. I don't know what we would binary search. Just like in any knapsack. And yeah, do be aware that in 9 minutes there will be EdCoder beginner contest. So that's this. The solution is roughly for every answer from 0 to n, for every mask from 0 to 2 to the power n minus 1, for every person to use next. If this person, so now we are looking at dp of answer mask, and now if mask doesn't include p, if p not in mask, and then we allow a transition, and either usually we will transition like this, ans, and here mask XOR 1 to the power 2 to the power p. That's likely what you want to do. What did I just do? Not sure. Okay, but it's too slow. And the final observation here is that actually when you have two options that are similar and they differ by the answer, then it's actually way more important than the current weight. So if you have option 1 where people, let's say 1 and 2 and so on are used, and you have, let's say, 2 full elevators, and third elevator is 20% used, and versus there is option 2, where the current answer is, maybe I will change the value a little bit, yeah, like that, where in option 2 the same mask of people is used, the answer is 4, and the fifth elevator, maybe current elevator, I will say current elevator is 20% used, let's say 2 out of 10, or here 8 out of 10, then obviously this is better. It's better to only send 2 full elevators and now build the third one, even if it's fully taken, because this is even strictly better than sending 3 full elevators, which is better than this, even if the difference is so small. So for every mask of people, you first of all minimize the answer, and second, you minimize the state of the current elevator. Here, by the way, there was no difference. Yeah, I could do or whatever. So the intended solution here is that dp of mask, and now it's very rare, but I will have pair of int, where this pair is number of full elevators, so the answer, comma, the state of the current one, the current weight. Or this is like answer, comma, current weight. 90% of the time you cannot do this. You cannot say that at the same time you minimize or maximize 2 things. But here, one is strictly more important than the other, and this is more of a tiebreaker. For a fixed mask of people already sent, you want to minimize number of elevators, and in case of a tie, where you have 2 ways of how to send them, and it's the same number of elevators, then you want to minimize the elevator that you are packing now. One more way to think about it is that those 2 values together, the answer and the 20% used, can be treated in your head as one fraction. This together is something like 3.2 of a full elevator. I don't recommend, you can theoretically here use double, but it's not recommended. But you can think about it this way. You're wondering how many elevators you need. It can be a fraction. Just remember that this means a new elevator 20% packed, where you cannot, if you have somebody that takes 0.9 of an elevator, so somebody's weight is 90% of the full capacity of elevator, you cannot say that this plus that is equal 4.1. No, because if you have 20% filled elevator, then this person doesn't fit. So if you want, you can think about this being a double, but it would require a lot of work and precision errors. Instead, this is the implementation, and the transition is that you iterate next person to use, and you check if that person with this current weight together will still fit in the same thing, or if not, you increase this value by 1 when doing the transition. Okay, add coder beginner contest in 3 minutes. Okay, so let's do the code. And I think then that will be stream over for today. There is n and there is x. X is capacity of one elevator allowed. There are W values. And now I want pair of int dp of 2 at power n. At the end, I will output dp of the full thing dot first. Let's say that this is the number of started elevators. Answer, so maybe dp dot first is the answer, meaning number of started elevators. By started, I mean at least somebody is there. dp dot second is the weight, how much of current elevator is used, possibly 0. I mean, for the question, there is a reason I keep this statement on the screen. My parameters, I think it's something like 191 or 2 and 94 kilograms. I hope this helps you in being better at competitive programming. And for the transitions, you iterate the mask. You here iterate the next person to use. If this if mask and this bit is on, then continue, then it's not allowed to do the transition. And here now, if this person is not yet used, then there are 2 cases. If dp of this mask, of the current mask dot second, plus the weight of this guy doesn't exceed x, that's one possibility, then I will transition to, I will say dp of mx or this guy or this. We minimize that with a pair of the same answer, so dp of me dot first and dp of me dot second. I type it so much that I prefer to make things. Answer is dp of m's first and current is dp of m's second. Yeah, I did change that at some point multiple years ago. Now, add coder contests, by the way, starts in less than 1 minute. It starts in 1 second. Good luck if you participate. I will not do it. So here, if the weight of current elevator plus this doesn't exceed, then you transition keeping the same answer and the current just simply increases by that much. And else, you minimize the new thing with answer plus 1. You start a new elevator, and here it's important, it only has this new guy. When I type minimum, I can have, for example, a helper function for that, just like I used today, add self. Well, it's supposed to work for pairs. There can be a general template for that. Okay, so I have a function, and then I will just say mini of this new state gets this value, or it gets this value. And are we done? We're not done. This is obviously a vector. I mean, there might be a way to do this with backtracking that happens to be fast enough, but it's not, you cannot prove its correctness. Plus weight of a person, weight, W, not A. Okay, and now, does it work? 0, beautiful. Why? Because everything is 0. I need to fill it with, let's say, n plus 1, n plus 1. This is like infinity, to be honest. This is infinity, n plus 1 elevators. And you start by saying this. So it means that the mask of 0 people I can send using 0 started elevators. Actually, yeah, this is kind of incorrect. Let's say 1 elevator is started and we have 0 of it used, but then all the future iterations will always have the current elevator to be at least partially used. This is the only this strange case where I have elevator used up to 0 amount. Seems to work. Accepted. Cool. Time complexity 2 at power n multiplied by n. Airplane sound. Interesting that you hear that. I hope that my microphone would hide such noises. Actually, it's when my window is open, you can hear a big street nearby, though it's far enough that it's more of a constant noise rather than suddenly you hear a car. Okay, I will talk a little bit more about the correctness of this. And then I think we'll finish the stream. First thing is that, fun fact, we could be given capacities of every elevator separately. Could be given x0, x1, and so on, capacities of different elevators. The solution would still work as long as you first sort. Then we would need to sort first, decreasingly, because you prioritize using big elevator. Other than that, everything would still work. That's a fun fact for you. And now a little bit more about the correctness, because it's not your standard DP. What happens here is that theoretically, the process of putting people in elevator, you can describe like this, where there are a lot of elevators available, and a step is that you take a single person and you put in some elevator. So the process might be like this. For every person 0 to n minus 1, decide to which elevator it goes. By the way, now I see sirens of ambulance, if you also hear it. I mean, sure, why would we do anything? Just use AI. Okay, so this is a process that if we are able to speed up with DP, then we're good. But I explained at the very beginning that this directly speeding up this with DP would mean storing current state of multiple elevators that we pack in parallel. That's tricky. Yes, it's an abstract problem, but multidimensional, so harder. I say that there is equivalent process that says for every elevator 0 to infinity, to however many you need, decide which people to put here. This is equivalent, and for example, it allowed us the solution with like 4 to the power n or 3 to the power n complexity, but also eventually we did n squared. And there is something even more, which is also equivalent, and also we use DP to speed this up. For for now. Keep repeating. Decide which person to put greedily in current elevator. If doesn't fit, then start new one. New elevator, I mean. What our final DP solution, the optimal intended solution, I think intended. Yes, they use pairs, so it's the same. This solution eventually is a DP speedup of this process, which is different than the first two. Here it says, keep repeating, decide which person to put now greedily in the current elevator. Because if you think about this as a real life, you can describe it like that. There is an elevator empty, you decide which person should go in. You decide which person should go in. And why would you now not put a new person in? Because you use somebody that is big enough that they will not fit now and they need the second elevator. So then you send the first elevator and the new one appears and you start packing. In particular, the brute force solution for this is n factorial. So there exists n factorial times n solution. Try all permutations. For every permutation of n people, put them greedily in elevators, just maintaining the two variables, the answer, how many elevators we started, and current weight, how much the current elevator is packed. And the final DP solution that we have is a speed up of this thing, of this process, and this brute force solution. Because if we try all permutations, then at every point it's only important which people were already used, which can be represented as a bit mask, and we have those two variables. DP is very often a way to turn something greedy or some kind of backtracking into DP by grabbing variables that those slow solutions would need and putting them as parts of our state. Though surprisingly here, the fact that we are already half through the permutation gives us a bit mask of people, and those, instead of putting them as a dimension of DP, we put as value of DP. So those two go as value, the pair of int, and the bit mask of which elements are already done in the, let's say, prefix of this permutation is the dimension. And do remember that this is very rare that we use a pair. I think that maybe 1% of problems, of DP problems, allows to minimize two things at the same time. Okay, it's very rare. Here we had a pair of answer current weight that we both minimized. This was possible only because one is strictly more important than the other, and the second was just a tiebreaker. If those are two almost independent parameters, you cannot say that you minimize both, because then you would have a hard time deciding about situation where answer is 5, current weight is 100, versus answer is 7, but current weight is 40. If you want to minimize answer, then this first option is better. If you minimize current weight, wait, what? I'm stupid, right? Yes, okay, never mind. If you minimize answer, then first option is better. If you minimize current weight, then second option is better. We could only do this here, so the DP for every state would know which option is preferred, and we could use minimum in the code, because we know that answer is more important, and this happens to be a second element, a tiebreaker, only for those situations. I'm happy that you think it sounds cool. Okay. So quite unique problem. Fine. We are what remains at some other day are those three things where I'm guessing that only the tilings problem is hard. So this will be the broken profile DP on a grid. Then digit DP. And what is this? Number of increasing subsequences. I'm guessing that that will be a segment tree with coordinate compression. Right. I may be counting tilings will be a separate stream itself or a video. Because it's just a big topic, the broken profile, and to properly explain it, you need some time. Or instead, maybe I will just do a stream where I solve both, well, when I solve all three, and without that much explanation, because for this there are other materials online. Yeah. You are welcome. All right, so I'm happy about what we did. We solved these 5 problems, from 2 sets up to elevator rides with, I think, a lot of explanation. Only for mountain range, I wasn't at first sure what solution they expect to make it easy and fast. My solution, my first solution, the one I came up with myself, was overcomplicated, the one with segment tree. Okay, you can still register for the Olympiad classes that are provided by Harbor Space for free for high school students. Eventually, they are meant to help you get to IOI, to improve your Olympiad performance. But there are 2 groups, and the easier one is at level of, let's say, this stream, where if you learned new things today, then it's very likely that you should attend the easy group, and if what was covered today is easy for you, then you should attend the hard group. The registration is ongoing. You will find the blog in Codeforces. I'm happy to hear that. Cool. Thanks to Harbor Space for sponsoring. Thank all of you for watching and commenting. I'm not thanking the person who just wrote something stupid in the chat. Yep. See you. Have a good day. I will do next stream on Monday, maybe. Maybe on Monday I will finish those things. We'll see. If not, then maybe